Hi, I'm David Christensen, and my project is on quadrotor trajectory tracking using LQR controller. And I implemented this controller based off a paper that was written by previous graduate students here at BYU. So just a quick recap on a LQR controller. LQR is really just a regulator, which is trying to drive the state to zero. So in order to control a system like a quadrotor, we need to use an error state LQR controller. So that way um, our desired state and our current state are driven to zero um, if we're using the error state. Um, so below you can see the cost to go function um, where we're driving the state to zero and also minimizing the control effort. And we know from what we know about LQR controller that the minimizing control will be this U defined by K and X, which we'll talk about again later. So one thing that's tricky about performing in error state with a quadrotor is that the attitude um, can't necessarily be defined by a vector. Easily like you would with position and velocity. So the states of our system uh, that will be the position of the quadrotor, its velocity, and its attitude. So sometimes people represent attitude as roll, pitch, and yaw, which is a vector, but subtracting them doesn't necessarily work out at linear conditions. Hover flight, stable, it kind of works, but it's not technically correct. So by using Lie group theory, we can get an accurate form of subtraction per se. If we convert the Lie group, the SO3 to its Lie algebra, we can perform some vector subtraction operations on it. So that's what we'll be doing here. And you can see it defined by this equation on the bottom right. So in order to get the error state LQR, we need to have some desired state and our current state. Our current state we get from the estimator and the system, but our desired state, we need to come up with some model to achieve this. So one thing that's important about quadrotors is they're differentially flat, which means that the required inputs to the system we can be fully defined using the derivatives of the outputs. So these inputs that we need, these desired inputs, the throttle, roll rate, pitch rate, and yaw rate, can be defined from the outputs of position, velocity, and attitude, and the desired trajectory. Yeah, so the input to our whole system will be some desired trajectory of our desired position, velocity, acceleration, jerk, heading, and the derivative of our heading. And then we can come up with this desired state that we're working with from these from this trajectory. So the desired state happens mostly by geometric thought and math. The throttle desired comes from using our equilibrium throttle divided by our gravity times the total acceleration desired. Sorry, the acceleration due to thrust that's desired. The attitude comes by just thinking about each column of the rotation matrix as the axis of the desired axis that we want. So for example, the downward z-axis of the quadrotor comes from the desired acceleration due to thrust that we want. Because the thrust will only happen in one direction on the quadrotor. So the negative direction of the thrust will be the downward direction of our quadrotor, which is also equal to our gravity minus the total acceleration of the quadrotor, which is given to us from our trajectory. And then the other two are defined. The y direction is defined by doing the cross product of what we just found with the heading direction. And then the x axis is defined by the cross product of the y and the z axis. And then our angular rates are defined using that attitude SO3 matrix multiplied by its derivative, and then taking a v operator over this. It's the opposite of a skew symmetric operator. Once we have that, we still need to represent our system as a state space system. So these equations define the dynamics of a quadrotor, which is nonlinear. So at each time step, we need to linearize the system in order to perform control with the LQR controller. So we know that the solution U comes from this K matrix, which is defined by R, B, and P. And to note, the R matrix and the Q matrix are weighting matrices that weight how much we value the error in our X and in our input. So these are matrices that we kind of tune, and to get a good start with it, we can actually use Bryson's rule, which is for each corresponding weight, it would equal 1 over the maximum value that we anticipate for that variable or input. But we know that to minimize this cost function, we need to solve the algebraic Riccati equation. We need to solve for P. By solving for P, we get the input U that minimizes J. So once we do that, then we get our error state input. Our error state input plus our desired input, which we calculated previously, gives us our final input to the system. So this is some simulations that I ran with a few different trajectories. This one is with fixed waypoints. And just a rotating heading. And here's a graph kind of showing that demo that we just saw. The north and the east directions deviate by average by about 0.2 meters. There is a kind of a constant offset in the down direction, which could probably be fixed by adding an integrator to the system. And the heading actually did really well in staying on its trajectory. This next one is a circular trajectory. and we're always facing the direction that we're going. So this one also did pretty good. The Y direction was pretty off at the beginning, so it had trouble getting on there onto its trajectory in the east direction. Again, the downward direction kind of had a constant offset, and the heading again did pretty well. It had some latency, but it stayed onto its intended trajectory. And the last one is just a figure-8 trajectory. Just to note, I did try to run these as fast as the Quadrotor could go to have like good performance. When I started going faster than this, it kind of had poorer performance. And then here's the last graphs of that, which I didn't do so well in the east direction on this one. I'm guessing just because I had it kind of going at its speed limit, the limits of its speed. It just overshot quite a bit. And yeah, it was supposed to be a constant heading as well. So you see some noise there, and then the altitude actually did pretty good, I'd say, for this one. Yeah, and that's my presentation. Thanks.